We might have gotten disconnected at the very end, so just a couple of minutes to finish step 4. So what we need to do here, we need to substitute equation 1 in equation 2. And so you'll find that y of s is equal to L of s times r minus h y. Now I'm just going to drop the s. So we can write that y times 1 plus LH is equal to RL. And since we're aiming for t, which is y over r, that is equal to L over 1 plus HL. Or now if we want to reintroduce the argument, it's L of s over 1 plus L of s times H of s. So this is a very common fundamental, I would say, expression for the closed loop transfer function, which you should learn by heart. And, L of s can be either just G of s if we don't have a controller, or GS times GC if we do have a controller, or if we also have the transfer function for the actuator is going to be the product of all of them. Just a very last thing, from now on, we're going to consider H of s equals 1. So in other words, we're not going to consider any interference due to the sensor while measuring the output Y of s. And if you do so, well, the systems are known as unity feedback control systems. So unity feedback control systems have a perfect sensor, or in other words, the transfer function associated with the sensor is equal to 1. So when we do that, then T of s reduces simply to L of s over 1 plus L of s. And one extra thing for you to verify is that if we instead had a positive feedback, in other words, if at the summing junction we had 2 pluses, then T of s would be L of s over 1 minus L of s. Now repeat steps from 1 to 4, and you'll find this minus sign popping up instead of the plus. Finally, you'll find here this block diagram reduction example, but Zara during the discussion will cover it, so you'll see it with her. All right, this is really all for today, and I'll see you next time. Take care.